Welcome back, everyone. We are in the week 9 problem solving session of the NPTEL course Control Engineering, and week 9 is about design using Bode Plots. I am Teja Golla, a fifth year research scholar working under Professor Santanu Kapat at Embedded Power Management Lab, IIT Kharagpur. Let me share my screen. I hope you can see my screen. So in the previous week, what we have discussed about the design using root locus. So in the week 8, we have discussed about design using root locus. Then in the week 9, now we'll be learning about the design using Bode plot. So what exactly we'll be dealing with here is the same design of lag as well as lead compensation as well as lag lead compensation. So we'll try to learn how to design the same lead, lag lead compensators using Bode plot. So in the last week we have discussed about the design using root locus, which is in a different domain. Now we'll be designing using Bode plot. So it's a different environment, but our overall final goal is the same, to design a controller so that it will meet the given requirements or the specifications, whatever the user is defined. So we'll have a system, we'll have some specifications, we need to design the compensator to meet the same. So the first question is, why are we learning multiple methods? Because it is always important to learn different methods, and for certain applications certain method may be easier or useful, and for different applications some other method may be useful or easier. So it's always important to learn all the methods so that we can correlate what exactly is happening in the root locus, what exactly is happening in Bode plot. So we are trying to do the same exercise using root locus as well as Bode plot. So it will also strengthen our concepts, as well as it will help us to correlate the concept between root locus and Bode plot. So we can cross check, or we can ask the question ourselves, like what we have done in the root locus and what are we doing in Bode plot. So we can correlate what exactly is happening in terms of the pole locations as well as the root locus plot, or what is happening in the Bode plot, and what are the design guidelines and how we are exactly approaching the solution or addressing the problem in different methods. So the final goal is set to design the control, to design the compensator. Okay, so I'll just briefly give the uh, transfer function again, because we have discussed in the last week. But for anyone who is going through this video, first we'll start with the lead compensator. So first thing we have told is it is to improve the, especially to improve the steady state. Sorry, it improve the transient. So lead is for transient, lag is for steady state, to improve the transient performance. And then two, phase is leading. Three, why phase is leading? Because zero is closer to the imaginary axis. Okay. So now this being said, what will be the transfer function here? So we can call GC of S will be, we have discussed in the last, Kc into S plus 1 by tau by S plus 1 by alpha into tau. Okay. Then same thing we can do for lag compensator. So how is it going to be different in this case? So here we are trying to improve the steady state performance. To improve the steady state performance, and then 2 phase is lagging here, means negative. And then 3, here pole is close because first the phase will start dipping. So pole is closer to pole is closer to the imaginary axis. GC of x will be here Kc into s plus 1 by tau as well as s plus 1 by beta into tau. And one more thing, here alpha is less than 1, because if alpha is less than 1, 1 by alpha is greater than 1, which means pole is farther away from the imaginary axis compared to the 0. Here beta is less than 1, which means 1 by beta, sorry, here beta is greater than 1, the opposite. So 1 by beta is less than 1, which means pole is closer to the imaginary axis than the 0. Now we are coming to lagging or lead lag compensator. So here it is to improve both the transient and steady state performance. That is the first point. Second point. First, initially phase is lagging. Initially phase is lagging, then leading. Because first the lag action will come, then the lead, followed by lead. And then it is a combination of lag and lead compensation. Okay. So coming to GC office, it's Kc into s plus 1 by tau, s plus 1 by alpha tau, into s, say tau 1, because we have two taus, 1 by tau 2, s plus 1 by beta tau 2, and then alpha is less than 1, and then beta is greater than 1. So this is how things are. And this is a quick summary about lead as well as lag compensator. Now let us dive into the design. So in this session also I'll be showing MATLAB as well as theory. So we need to understand the theory as well as simulate it and check the MATLAB so that we can try to understand the concepts better. Also, we can correlate what exactly is happening. So we can have a visualization of what exactly is happening. So lead compensation. So as we know, the GC of S is Kc into S plus, say tau, I am calling it as T, so that it will be the same representation what sir has used. So now it will be alpha into Kc into 1 plus Ts by 1 plus alpha Ts, right? So I can call this as some K. So now what I'll be getting? I'll be getting GC of j omega is equals to K into 1 plus S 1 plus j omega, because we have converted j omega t by 1 plus j omega alpha into t. So this is the expression that we got. So now let us see, before we even design, let us see how it will look like. Although we have discussed it, I'll just again show the quick MATLAB simulation of how exactly it is going to look, so that we can have better visualization. So here I have these MATLAB codes. Again, I'll be uploading this so you can play with this and try to understand. So I'll explain the MATLAB code quickly. In the beginning, we have the clear CLC as well as closure. By this time, I think you will be understanding what this means. They are just to clean the command window workspace as well as close any figures if they are open. And then I am defining a variable T1. So, or let me do it as T. So I have T, and then instead of alpha, I am considering multiple alpha. So I have named it as alpha 1, alpha 2, alpha 3, alpha 4. So I am defining the transfer function g lead 1, g lead 2, g lead 3, and g lead 4, which is 1 plus s into t, 1 plus s into alpha into t, and alpha is alpha 1, alpha 2, alpha 3, and alpha 4. Now, this is the Bode plot code that we have already discussed in the earlier week. So it is just the same code. And this is a figure 1. I am plotting the Bode plot all in the same plot and see how the Bode plot is varying if I have different alpha. So how it is varying or what exactly it is causing the change or where it is causing the change, how it is going to get affected. And in all these cases, I have chosen k to be 1, but k can be chosen anything. Just to consider the same k, I have considered k to be 1 for the time being, but you can consider different k and see how things are changing. And I am also naming the legend, so we'll know which is corresponding to what exactly. So this is the Bode diagram. If you see, as alpha is becoming smaller, the phase lead that it will provide is more. If I have a larger alpha or close to 1, the phase lead is less. So you can see the peak phase is happening at different locations for different alpha. I have considered T to be same. So the T is same, but alpha is different, which means the pole location is, if we go back here, the pole location is varying, whereas the zero location is the same. Only I'm varying the pole location. So that's why it is having this kind of behavior. And then if you see the frequency at which this peak is happening is different. Also, the peaking behavior is also different. So what I will do is I'll just a minute. What I will do is I can add this in the I'll also add this in the here so that you can understand. Let me see if I can copy this. I think it is clipping. So what I can do is I can just make it something like this. I think this should go. This is fine. Yeah. So this, if this is in the notes, then we can cross check rather than doing the MATLAB again. So this I think would be helpful for you. So that's why I'm trying to do this. Yeah. So now if you see, the peaking is dependent on the alpha, right? Depending upon the alpha, the maximum phase that it can provide, phase boost it can provide is varying, and also the frequency that it is happening is different. So we are calling this maximum phase as phase maximum, and then omega m is the frequency at which this phi m is happening. Similarly, this is its phi m, and then this is its omega m. Similarly, this is its phi m, this is its omega, this is this phi m, this is this omega. And as we can see, this phi m and omega m both are dependent on alpha. So if we write the expression, we'll get omega m. So these are very important. Omega m is 1 by root alpha into t, the frequency that it is happening, and phi m is sine inverse 1 minus alpha by 1 plus alpha. And if you see at this frequency, if I extend, what will be the magnitude of the system? What will be the magnitude of the this magnitude plot? So that is given by mod gj omega at omega equals to omega m is nothing but 20 log 1 by root alpha. So depending upon our alpha, so whatever is the requirement, how much phase is needed, accordingly we can select this alpha as well as t depending upon our requirement, omega m, phi m, all these things. So that's why this is very important. So in this way, we can get the information regarding where the peaking is happening, and also how much is the phase boost that we can provide. So why is this important, or how it is going to help? So now let us solve one problem and then we can correlate. So what we have learned is when we are doing lead compensation, we will get this transfer function, and if we draw the Bode plot for different alpha, I can see that the maximum phase peak for each alpha as well as the frequency at which it is happening is function of alpha, and then these are the expressions that we can get. So now using this information, I will have to design a compensator so that I'll be meeting the given requirements. And this is the information that I have. So now using this, how am I going to design? So one more thing, in this design criteria, we'll always be designing the, so I'll just give the guidelines so that, sorry, when we design it actually, guidelines, when we actually design it, we can follow. So here first always design the steady state error parameter. So always design gain k first of this compensator, gain k. Okay. And then draw the Bode plot of k into that plant G. And then check the phase margin, bandwidth, phase margin, PM, bandwidth, BW, as well as gain margin. And then see. Now you can see what is the, you can understand what is phi m, what is omega m, and from this we can get alpha as well as t based on our requirement, more or less. Also, you can also see what is mod gj omega at that omega m. And then from this, now once you get this, now calculate alpha and t. Calculate alpha and t, which will give me my GC, right? This will give my GC, but also we have to cross check. Once draw the Bode plot, draw the Bode plot of G times GC, and then you cross check. Cross check if the requirements are meeting. If they are not meeting, if no, then again you have to redesign. So we'll be doing this with an example. So coming to our first problem, the lead compensation, I have given a plant G of S is 4 by S into S plus 2. And the desired specifications are KV should be 20 into second inverse, 20 second inverse, and phase margin should be at least 50 degrees, and bandwidth should be at least 8 radians per second. So now let us see. Here I have given it is lead compensation. So let us assume that we are dealing with the lead compensation. Okay. So first I'll write the expression for the lead compensation. GC of j omega is k into 1 plus j omega t by 1 plus j omega alpha t. Okay. So first we'll start with the gain, whatever we have put design guidelines. So first thing what I'll do is I'll see how much is my gain k. So if I have to calculate kV, I'll get limit s tends to 0, s into g of s into k. So if I calculate this, I'll get 4k by 2, which is equals to 20. That implies my k is equals to 10. Okay. So I got my k. What is the second step that I have told? Draw the Bode plot of k into g. This is our plant into the gain. So let us see. First, I'll also tell you the code that I have written for the lead compensation using Bode plot. Again, clearing the workspace as well as command window. Then I'm defining the transfer function 4 into s by s plus 2. My desired specifications are kV desired is 20, and then phase margin is 50, bandwidth is at least 8, right? So let this be 8. Okay. So what I have to do is first calculate my KC. And what is my KC? KC is KV desired by the gain my system has. So if I evaluate till here, If I'm evaluating till here, I will get my KCS 10, which is what we have calculated. Now draw the Bode plot of K into G so that I will see how much is the phase margin of my system K into G without any compensation, only gain compensation. How much additional phase is needed, at what frequency it is needed. So that based on that, I can choose my phi m, I can choose my omega m, and then I can design the compensator. And then once I design the compensator, I'll cross check whether it is matching or not, or I'll redesign. So it is an iterative process, just like how sir has mentioned. And then we have to do it in an iterative way. So the understanding of the code as well as the concept is very, very critical. Okay, so here I have, let us plot this G into KC. So I'll come back to this code, I am designing. But before that, let us plot K into GC. So things are going to get interesting from here on. Yeah, so characteristics. Okay. So if you see, the phase margin is 18 and then frequency or the bandwidth is 6.17, which is more or less okay. So let me consider this plot. Okay, so let me take a screenshot. Why I'm doing this, I'll let you know, because these things are very critical. What we are doing, why we are doing it is very important, else you'll not be able to understand what is going on. Okay. Okay, I think I'll take a full picture in the center. So if you see, when there is phi m, the gain is increasing to certain value, right? So basically what we are trying to do is, I'll use a pink color. Our compensation will provide a peak here, so in this way, and then also it will have gain increment, right? So what exactly should happen? My phase margin will be calculated at gain crossover frequency, right? So at that gain crossover frequency, I have to provide additional phase. So choosing this frequency at which we are providing the phase is very important, because say if at this frequency, current gain crossover frequency, if I am providing phase phi m, at that phi m or at that omega m, I will also have some gain that is coming from the compensator, because that is what we have seen. Mod gg omega is also having some gain, right? But I want my phase margin at the gain crossover frequency, right? So if it has certain gain over here, then the gain crossover frequency will not happen at this, right? The gain crossover frequency will happen when the gain is 0. So because there is an additional gain due to this compensation, I have to choose that frequency where there will be a negative magnitude of this gain, so that both will get cancelled. What I am trying to say is, so that's why it is very important to understand what is going on. Yeah. So if I push it further, okay. So if I push it further and then say I have my peak behavior somewhere, oh, sorry. So I have a peak behavior somewhere like this, okay. And then now it is something like this, right? So now this positive, so whatever is this positive and whatever is this negative, say if they together becomes 0, then the compensated plot will go through like this, right? So I have to add phase at the gain crossover frequency. So I have to choose that omega m where this magnitude of the compensated of the of this compensator and the open loop plant, or I should say K into GC, will get cancelled and will result in 0 gain, because at that 0 gain only I'm calculating the phase margin. So my omega n should be at that region where I will get this magnitude but negative, because at phi m I am having this magnitude that is coming from the compensator. This positive value should be added with the negative value of the plant, so that that will result in 0 dB gain. So first I have to calculate this 20 log 1 by root alpha, but for that I need alpha. So we'll choose phi m. So how do we choose phi m? how much additional phase I am going to provide at this additional phase I'm going to provide at this phase margin. So currently how much is the phase margin? 18. So how much additional phase margin am I going to provide? So that is what we are looking now. So currently phase margin is 18. My desired is 50. So my 5M will become 5M will be desired 50 degrees minus this current phase margin 18 degrees. So this much addition I am going to be needing, right? So it will be resulting in 5M is equals to 32 degrees. But if you see, my phase margin is not happening to this. It is happening somewhere at this point, right? So I might have to create an additional phase, not just 32 degrees. So for the, because there is a decrement in this gain, right? I am adding 5M at this point. So it is not exactly 18 degrees, but it is less than 80 degrees. So we can consider 5 degrees to be our correction factor because we do not know exactly where we are adding. So we can consider 5 degrees or 10 degrees, 5 to 10 degrees as our correction. So now if you do that, I'll get my 5M to be 37 degrees. Why we have done that? Because we are not exactly adding at this point at 18 degrees phase margin, because our gain crossover frequency will be somewhere on the right side. So there the phase that is needed will be lesser, right? Because for this 18, if I add 32, then it will give me 50 degrees phase margin. But I gain crossover frequency is not going to be here. It will be somewhere on the right side where I will be needing more additional phase. So correction factor we have considered 5 degrees, which will result in a phase margin of 37 degrees. So now for this 37 degrees phase margin, phi m is equals to sine inverse 1 minus alpha by. So phi m is equals to sine inverse 1 minus alpha by 1 plus alpha. So now you have to calculate what is my alpha. So again, I have written the MATLAB code just to avoid the calculations. So I am giving my phi m. So what I have done is I have written the code. How much is the phi m that is needed? So my phi m that is needed is 32 degrees. But to this 32 degrees, I am adding a correction factor of 5 degrees. We can add from 5 to 10 degrees. Say 5 is not sufficient. Then we'll reiterate and maybe increase 10 degrees. So we have to do it in an iterative way. We'll design, check if it is meeting the requirements. Say if it is not, then we'll go back again, redesign. But first we'll always design the gain of the compensator to meet the steady state. Then we'll do the lead compensator, pole and zero locations. Okay. So I have got my phi m. Now alpha is nothing but 1 minus sine phi m by 1 plus sine phi m. So alpha is nothing but alpha is equals to 1 minus sine phi m. But why I have written sine d there? Because it is in degrees. So that is the MATLAB command 1 plus sine phi m. Okay, alpha is 1 minus sine phi m by 1 plus sine phi m. So let me calculate phi m, which is 37 degrees that I have considered, as I have mentioned, 5 degrees for correction, because my gain crossover frequency is not at this point. It is somewhere right side where I will be needing some more additional phase. So that phase I'm considering 5 degrees for the time being. Okay, once we do this, now how much is the additional gain that I am going to need? Because if you see, let us come back to this. So here this at this phi m, I will be getting an additional at this phi m, I'll be getting an additional gain as well, right? But that gain should be added with the negative gain of this plant, should be added with the negative gain of this plant, so that overall the gain will become zero. So only when the gain becomes zero, we call it gain crossover frequency. So we are trying to make that point as gain crossover frequency. So how much gain that we will be getting from the compensator should be added with the negative gain of this plant, so that it will be becoming zero, and that will become our gain crossover frequency. So now we are going to use this second formula, which is mod g of j omega is 20 log 1 by root alpha. Okay. So how much additional gain that we are going to get? Mod g j omega, omega equals to omega m, is 20 log 1 by root alpha. And then we have already calculated alpha from our phi m. Phi m is given, so I can calculate alpha. Once I have calculated alpha, I can get this additional gain the compensator is providing. So I have written the MATLAB code for that. So additional gain that the compensator is providing is 20 log inverse of square root of alpha. So it is 20 log 1 by root alpha. So now if I get this additional gain that the compensator is providing, what I have to do, say, let me go back here. So if this, say this is resulting in mod g, say magnitude, certain magnitude. Now I have to find that point in the plant where I will have negative g minus mod g. So I have to find that frequency, this frequency, where I will have the negative magnitude of what my compensator is providing. So I should draw from the magnitude plot. So my magnitude plot will be somewhere like this, right? So at this phi m, whatever is my mod g, this should have minus mod g, right? So then the summation will become 0 and then we can call it the gain crossover frequency. So I have to find that frequency where my uncompensated plant Bode plot will result in the magnitude of minus mod g, and then this will become my omega n. So basically what we are trying to do is we are checking how much additional phase my compensator has to provide, phi m. From that phi m, I will get alpha, and then from that alpha, I'll also get how much gain my compensator is providing. So now I'll go to that frequency where my plant will provide the negative of that additional gain, so that summation will become 0, and then this omega m will be nothing but my omega gain crossover frequency, because it will result in 0 dB, because this will result in 0 dB, right? So I am fixing my gain crossover frequency. So how much is my mod g? If you go back and calculate this, my additional gain, how much is my additional gain? How much is my additional? It is 6 dB. Sorry. So it is resulting in 6 dB. So my compensator is resulting in 6 dB. Now I have to find omega such that, which will be omega, such that my k into g, this Bode plot, has a magnitude of minus 6 dB, so that the summation of these two will become 0 dB, resulting in gain crossover frequency. So now we have to manually find where is this minus 6 dB. So I can click it and then drop it. I need minus 6 dB. So it need not be exact. It can be in the vicinity of that. Say it is minus 6.09. I am getting 8.87. And for the sake of understanding, I'll attach this screenshot so that when you go through the video later, you will not have any confusion. So I'll also attach this screenshot. Yeah. So now I have found where I will get minus 6 dB, so that when added with the compensator, this will become 0 dB. So now this frequency that I am looking for, 8.87, this will be my omega n, because where I'm expecting maximum phase, and from this formula I can get omega m is 1 by root alpha t. So now this omega m is equals to 1 by square root of alpha into t, is nothing but 8.87, and alpha is already calculated from phi m. So how much is my t? So this is what I'm trying to calculate now, t. Once I get t, my compensator alpha and t are known, as well as k is known, because I have calculated from the steady state error equation that whatever the user has selected, kv should be 20. Okay, so I have again written the equation in MATLAB to calculate. So I have feeded omega m to be 8.82 when I have done before the class. Now I'm getting 8.87. So let us put 8.87. Here I have written a comment so that you have to find the frequency corresponding to the negative of this additional gain. So that this frequency is at, this is the frequency at which phi m occurs, and that frequency we have defined as omega m. So omega m is known. and then T is 1 by omega m square root of alpha. Once I get T, alpha is calculated, Kc is calculated. This is my Gc. So once I get Gc, what I have told in the design guidelines, let me go back here. Sorry. Once I get the Gc, I have obtained phi m omega m as well as this mod gj omega. I'll calculate alpha and t and then get gc. Once I draw the Bode plot of g into gc, I'll have to cross check whether it is meeting the requirements. If no, then I have to tweak the design a little bit here and there, or I have to tweak this correction term that I have added and then make sure that the design will meet the requirements. So I'll plot the g into gc. So this equation, this line I have initially commented on. Now I'll uncomment it. So I'm plotting two. One is G into Kc, which is only gain compensated. I am calling it as uncompensated. The other one is G into Gc, which I'm calling it as compensated. So now let us run and then let us see the characteristics. So the blue one is the uncompensated, where I have phase margin at 18. Phase margin at 6.17 radians per second, and then it is 18 degrees. Now I have designed compensator, and then phase margin is around 49.8 degrees. So it is coming to be close to 50 degrees. And then the frequency at which it is happening is 8.84 radians per second. If you see, I have added the phase boost here. So if you see, there is a phase increment over here. And then this also has shifted a little bit right side because the compensator has this additional gain, right? So the compensator has this additional gain characteristics. So that is making this little bit move right side. So that is why the Bode plot is looking something like this. And then we are trying to force this omega m to be my gain crossover frequency. And this is the gain crossover frequency at which phase margin is 49.8. So the correction term that I have added is 5 degrees. Say if I have added 6 degrees or 8 degrees, then I'll be able to cross this phase margin more than 50 degrees. So that thing we can again do. So let us save this in the, let us do that practice also. I think the snipping tool is creating the issue. Let me figure it out. So I have gotten my T, and then this is the Bode diagram that I'm getting, and I'm getting my phase margin to be 49.8 degrees. So this is my, if I have considered a correction factor of 5 degrees, this is the correction factor that I have considered. What if I increase correction factor? So what if I consider correction factor to be say 8 degrees, say my correction time? I'm considering to be 8 degrees. So let me redo it. So if I have the MATLAB code, I know what to do. So first I'll calculate this to be 8. Okay. And then I'll calculate my additional gain. So I'll run the code till here. So I am getting now 6.63 as my additional gain that I need. So I have to choose that frequency, which will result in minus 6.63. So I'll plot only the Bode plot of K into GC. So I have to choose minus 6.63. So let us check that. This is the one what we have. Now I have to choose minus 6.63. 6.66 in the vicinity is fine. So my frequency is now 9.17. So let me do, I think what I can do is I'll write this. This is 5 degrees correction. And if I go down, this is 8 degrees correction. And then it is coming 9.17. So this is my 9.17. And then I'll uncomment this and I'll see how much is my phase margin. So all stability margins. So now if you see, it has increased to 52 degrees, and which is what exactly I'm looking for, because I have assumed my correction factor to be 5 degrees and then it is not sufficient. So I will tweak the correction term and then follow the same exact process and then see whether my design criteria is meeting or not. So if you go back, my design criteria says KV is 20-second inverse. From there, I have calculated the gain K, and my phase margin should be at least 50 degrees. So it is 50 degrees, and gain crossover frequency is 9 radians per second. Now, if you plot the closed loop transfer function, it will be slightly more than this, what sir has mentioned. So it is also meeting. So my all criteria are meeting when I'm uh, uh, considering a correction term of 8 degrees. So if I increase it further, then my phase margin will be slightly better. So you can also plot the step response and see whether it is fine or not. And then step response we have considered in the previous week, so we can consider that as well. So no scripts. There is some issue with my snipping tool. So I think that's okay. So with correction term, whatever I'm getting. So with the correction term, I'm able to meet the given requirement. So in this way, we can design the controller. So now the design requirements are known. So just to quickly summarize the code, what we are doing in the case of lead compensation design is first we have to define the transfer function, and then based on the desired specifications, first I have to calculate the gain. So I'm calculating the gain of the plant, and then how much additional gain is needed to achieve the desired KV. From the here I'll get KC, and I am calculating the phase margin from this command of G into KC with the gain, and then I'm seeing how much additional phase I'm needing plus a correction factor. And then from this 5M, I'm calculating alpha and the additional gain caused by this compensator. And now I have to find the frequency at which negative of this additional gain is caused by K into GC. So that effective will be 0 dB. And then for that omega M, I am calculating T, GC, and then I'm plotting the Bode plot so that I'll be getting the overall transfer function and then the Bode plot of the transfer function. So I can cross check whether my design requirements are meeting or not. So in this way, we'll be doing the lead compensation design. Now we can move to the lag compensation design. So similar to the lead compensation design, I'll just copy paste this. So in the case of lead compensation, we also know that our alpha will be less than 1, and then in the case of in the case of lead, it is less than 1, and here we don't call it alpha, we'll call it beta. This will be beta, this will be beta, and this also will be beta. So this will be my beta into T, this will be beta TS, and then this will be beta T, and we know that beta is greater than 1. So in the same way, how we have done for the lead compensation, first let us see the effect of beta on the Bode diagram. So we'll be looking at the same. So I have a Bode plot of lag. What I have done is first I'm clearing the workspace command window as well as closing all the plots. Then I have assumed T1 to be 0.1. If you remember in the root locus also, we have started with T1 to be 0.1. We have not defined as such, but we have considered that very close to the imaginary axis, and from there we have calculated the beta, and beta is greater than 1. So I'm calculating considering from 2 to 10, I'm seeing how the beta is going to affect my lag, whatever lag that I'm aiming for. And this G lag is 1 plus ht1 by 1 plus s beta t1, and I have 4 such transfer functions, and I'm also having the Bode plot command, and I'm plotting all on top of each other, and I'm also calculating the beta value and adding it as a legend. So if you see over here, this Bode diagram, For beta equals to 2, the phase lag is lesser, and for beta equals to 3, the phase lag is more, just like the opposite of what we have achieved in the lead compensation. And for beta equals to 10, phase lag is the maximum, and just like the opposite of what we are getting in the lead compensation. And here it will start with 0, and then here it is ending at certain gain. If you calculate that, that will be 20 log 1 by beta. So let me take a screenshot of this. I'm not sure why it is not snipping. Okay. In that case, I'll save it as PNG. Save. So this is lag Bode plot. Then I'll save it as PNG. Save. So now this is the effect of beta. And then here the design criteria will be something slightly different, but we'll also see what are the guidelines. The guidelines will remain more or less the same. And if you see, this will be 20 log 1 by beta. So this gain at which it is settling is 20 log 1 by beta. Okay, and now we'll see how we'll be using this 20 log 1 by beta. So as sir has mentioned, we'll be only designing beta, and then we'll consider tau t to be a guess starting with t equal to 0.1 and see whether the design criteria are meeting or not. And then we'll see whether it is meeting. Else we will tweak the t little bit and then check. So if we discuss about the design guidelines. First again, we'll have to find the gain k. Find gain k using the steady state error specification using the steady state error specifications. Once we get this k, then we will draw the Bode plot, same, exact same Bode plot of k into g supplied, and then check the phase margin as well as gain margin and bandwidth, whatever we are getting. Phase margin, we'll check the all the margins, gain margin, then gain crossover frequency. And based on that, we have to take a call. In the case of lead, we are calculating how much phase is needed, where the frequency is needed. But in this case, we are going to do it a little bit opposite. We will be taking how much gain we have to reduce. Okay, so what we are doing here is a little bit slightly different. So basically we have to find 20 log 1 by beta. So we'll get there. First we'll have to calculate beta. So from where we are calculating, we have to see how much we will be subtracting, or because since this is a negative gain, this negative gain will be added to the plan. So how much negative gain will be added to the plan? So that we have to check from the plan. So how much decrement in the gain? Decrement in the gain is required. So we'll see how much is this required. From there we can get beta. So calculate beta. Calculate beta. And once beta is calculated, check the Bode plot of GC into G, and then once this is whether this is meeting the requirements or not. That this is meeting the requirements or not. Say if it is not meeting the requirements, if no, then we'll redesign. We'll redesign, and then we will see whether we are meeting the requirement. So again, it's an iterative process. If you do not meet, just like in the case of lead compensation, what we have done, we have iterated. We have realized that it is close to 50, but not 50 because we have said at least 50. So we have increased the correction term. Say if this is also not sufficient, we have to further increase. So we have to do it in an iterative process until we reach the desired specifications. So let us solve one problem quickly. So here I have considered one such problem where my g of s is given as 1 by s into s plus 1, 0.5 s plus 1. So first again, what is the lag compensation transfer function? It is gc of s is equals to k into 1 plus j omega t by 1 plus j omega beta into t. So now we know that beta is greater than 1, and always it's a sign that if you are not getting beta greater than 1, it means you have made a mistake. So then we have to cross check what exactly is going wrong. Okay, first let us design K. So from the first design specification, I know that limit s tends to 0, s into k into gc of s or g, s into k into g should be equal to kv. So if you calculate, we'll get kv is nothing but k by 1, and that is given as k, 5. So my k is 5. So from here, I got my k as 5 from the steady state error specifications. And if you see the design guideline, now we have to see the Bode plot of k into g. So just like the lead compensation, let me close this. I have written the Verilog code for the lag compensation as well. So sorry, this is lead. I have to open lag. Yeah. I'm cleaning the command window, clearing the workspace, as well as closing all the figures that are open. Then I'm defining the transfer function, which is 1 by s into s plus 1 into 0.5 s plus 1. And the desired specifications are same as kV desired as 5, phase margin is 40 degrees, gain margin is at least 10 dB. So if you go back to the code, let's close this. 5, 40, and then 8. So what I have done is the same thing. First, I'm calculating the open loop plant gain when it is multiplied by G, and then how much additional gain is needed to meet the desired kV. So if you calculate till this point, I'll get my KC as 5, which is what we have exactly calculated. So I have written some comments here, but before that, let us quickly plot K into GC and then see what is going on. Okay, so if you see, my open loop plant is like without any additional compensation, it is unstable. And then the phase margin is coming to be minus 13 degrees at this. Okay, so what exactly we will be doing is how much phase margin do I need? So I will be needing at least 40 degrees. And again, here also we have to consider around 10%, what do you say, 10% correction factor. And then we'll be targeting for 50 degrees so that in the meantime, we'll get around 40 degrees. So what we will be doing is, so let me consider one point over here. So I will consider a phase that will be resulting in, okay, I think I have to explain. So first let me save this. So what I'm going to do. Okay. So if you see this plot, I am taking advantage of this negative gain, and then I will add this to the uncompensated plant so that my gain will be reduced. So this is my uncompensated plant. So what I'll be doing is, whatever I have, sorry, it is starting from 0 and then it is settling at a negative value, right? So what I will try to do is, I will try to add this to my uncompensated plan. So effectively, I'll be getting something like this. So what I'll be doing is, I'll be pushing my gain crossover frequency from this point to some point, right? And then how do I choose this point? So how do I know this is the gain crossover frequency? right? So I have to choose that gain. I have to choose this. So now I have to choose that omega. So I have to choose that omega over here. How do I choose? So that the phase corresponding to this omega, this is my phase margin, right? So this requirement is met. So I have to choose that omega so that at that omega, the phase corresponds to my phase margin, because now this is my gain crossover frequency. So because this is my now new gain crossover frequency, my phase margin will occur over there. So I have to see how much phase margin do I need. And then at that point, I will see what is my omega. So, and how much decrement. So basically we are trying to reduce this, right? So we are trying to reduce this gain to 0. So this, whatever we are trying to do, the decrement in the gain. So this decrement in the gain, we are trying to force the gain to become 0, so that that will be my new gain crossover frequency. And then there I will get my phase margin. So I'm first fixing my phase margin and then checking my omega, and that omega, at that omega I'm checking how much decrement is needed in the gain, because that decrement will be provided by this. So this guy will provide the decrement in the gain. So this guy is the decrement in the gain. Okay. So again here, let us start without any correction factor and let us see, because similar to what we are doing, say the phase will also be looking something like this, right? Some lag and then 0. So at this region, there will be some phase lag. So there will be some phase lag, and then that's why we need to consider correction. So this is the reason why we need correction term. In the case of lead, because the gain crossover frequency is slightly towards the right side, it is shifting towards the right side, where we will be needing additional phase other than what we will be needing at this point. So the two reasons are different. So here our gain crossover frequency is slightly shifted toward right side. So whatever phase that we'll be needing at this point will be lesser than what we'll be needing when the crossover frequency is shifted towards the right side. So that is the reason why we are considering the correction term, and then it will be typically from 5 to 10 degrees. Whereas here, our lag compensator will provide an additional phase lag at the point where we are trying to get this gain crossover frequency, so that this has to be considered by the correction term, and we'll be considering around 10 degrees, whatever sir has mentioned. So let us consider around 10 degrees correction term. So first what I have to do is, I have to see at which frequency my phase margin is meeting. So my phase margin is given at least 10 degrees. So my phase margin point. So now the third point, I have to find out how much decrement in the gain is needed. So what I will be doing is, my phase margin, I will target that point where I'll have my 10 degrees. That will make it 50 degrees. So 50 degrees short of minus 180 degrees. So let us see. Yes, got it. So I'm running the lag compensation. Something is not correct. K into Kc into G. So what is my Kc? 5. So now I'm drawing the Bode plot. Something is not correct. Let's check. Let me restart my MATLAB. I think that's the issue. We are in the lag compensation of Bode plot. Okay, so we have to check that omega where our phase margin requirement is meeting, and then at that omega we'll see the magnitude of the uncompensated plant, and then we'll see how much we need to decrease that gain so that it will be made zero. So it is slightly different from what we have done in the lead compensator. So it is very important to correlate what exactly is happening and why do we need this correction term, because we are not just randomly putting, we just have to understand why it is needed, and then now we'll be understanding what is going on and what has to be changed so that our requirement is basically met. So MATLAB is opening, just give me some time. Okay, so this is the code that we have. Now we have to draw the Bode plot of the K into GC and then see where I am getting that phase margin, and that at that phase margin, how much is the decrement in the gain that I should be doing. And there's some issue with my MATLAB. I think there seems to be some problem. I'll restart the meeting and see whether it is uh, the meeting issue or whether my laptop is getting loaded. I'll try to end the meeting and I'll rejoin so that uh, I'll see whether it is causing an issue or not. Just try to rejoin and restart the meeting. Okay, I think for some reason when I'm sharing my screen, it is not running. Okay, now it is running. Let me reshare the screen. Okay, so I hope you can see my screen. So what exactly is happening over here? Uh, I need to find that frequency where my phase margin will result in 50 degrees. So I'll select that region uh, where is 50 degrees means around 110. Sorry, not 110. To result in 130 degrees. So this is the phase at which I'll have a phase margin of 50 degrees with the correction term. And then my frequency is 0.486. So I'll see at 0.486, 487, 486, I need a magnitude of how much? 0.486. 19.1. Say 19.1 magnitude has to be reduced. So I'll also save this. I think my laptop is facing the issues with the graphics. So bear with me. Okay. So this will provide me how much decrement in the magnitude that I need that will be caused by this lag compensator. So how much decrement I need? 19.1. So I got magnitude decrement or gain decrement. Gain decrement caused by that should be 19.1, or it should correspond to minus 19.1. So the compensator will provide this, right? So which is what exactly we are discussing. 20 log 1 by beta will cause that decrement so that my gain will become 0, and then that will become my new gain crossover frequency, and then that will result in the phase margin. So if this is my decrement that has to be provided by the compensator, so I can say that 20 log 1 by b 4. So this is the point number 4. Point number 4. So 20 log 1 by beta is corresponding to minus 19.1 dB, and I have to calculate beta. So what is my beta? So how much is my beta? So again, I have written the MATLAB code. Let us see. It is running, but I think figure is facing some issue. Okay, let it be. I will not close out so that let us see if it will plot on the same. Okay, so this is the one I'm talking about. Find the frequency corresponding to the desired phase margin, and then find the gain reduction required at this phase margin, whatever is that requirement at this, I think, frequency. So first we are finding how much phase margin we need plus correction term, and wherever it is happening, there we are trying to reduce the gain using this lag compensator. And then how much did I get? I got 19.1 dB. So if my reduction is say 19.1, I am calculating my beta. So gain reduction that needs to be achieved by this lag compensator is minus 19.1 dB. So if I calculate beta, then this is the expression that I will be getting, inverse of 10 into gain reduction by 20. So once I calculate beta, as I have mentioned, T we are considering 0.1 as an initial guess, and then we are calculating GC. And once we are calculating GC, what I have said, I have told in my design guidelines that once you get the beta, draw the Bode plot and see. So once I got my beta, let us see how much beta I am getting. So if I run this, my beta is 9, which is above 1. So my calculation is correct. I am getting beta to be 9. So once I get this, I have to run the Bode or draw the Bode plot of K into, sorry, not K, now it is not K anymore. Now GC into G, and then we have to check whether it meets the requirements. Okay, so let us draw the same, and hopefully my MATLAB will show the plot. Yeah, luckily it is showing. Glad. So let me remove this. Okay, so the yellow is the uncompensated. I think it has messed up. So let us hope it's not the drawing. Let me stop sharing and then run it and then reshare. Not sure about this problem. It is removed. Okay, so it has drawn. And then if I see the stability margins, the blue color is the uncompensated, where I got my phase margin to be minus 13 negative, and closed loop is not stable. Now whatever I have gotten my phase margin to be 39.7. I have designed to be 40 degrees, and I have considered a correction factor of 10 degrees, and I got 39.7. And then if you see, my gain margin is 13.4, which is what I am expecting. How much did I get? I am expecting 10 dB. Phase margin should be at least 40 degrees, and then I am expecting 10 dB, but it didn't happen. So what I'm going to do is, let me add this. Say if I want more than 40 degrees, then I have to slightly improve my correction term. I have considered 10 degrees. Let me consider 12 degrees and see what will happen. So this is my third picture in lag design. Okay. So my lag design is over, and then I am trying to slightly improve the response, because I got what did I get? I got 39.7, 39.7 as well as 13.4. So this is okay. This is matching, but I need this to be slightly more. So now This has been obtained for the 10 degrees correction. Now what I will do is I'll consider 12 degrees correction. 12 degrees correction, which means I am targeting for a phase margin of, instead of 40 plus 10, now I'll have 40 plus 12 degrees, which is equals to 52 degrees. So now I'll consider that where I'll be having, instead of 130, 128 degrees. So let us, did I close? Okay. I have to probably stop sharing, run it and then reshare. So now I have to see at which I am getting 128 degrees, because I am now targeting for 52 degrees. So I'll see 128. It is 0.461 is my frequency. At 0.461, 0.461. 19.7 is the reduction in the gain that I'm going to need. So for this, let us check. So this is what I'm getting. For 0.46, I'm getting 19.7. So let me go back to the code, 19.7. So this is for 10%, 10% reduction. Now I am targeting 12% reduction and I got 19.7. So I'll comment this out. I got 19.7 and I'm considering 12% reduction. And again, I think I have to stop sharing. Sorry for the convenience. Let me run it and then start resharing. Okay. So once I got the response, if I see now, my phase margin of the compensated has slightly increased 2 degrees. Now it has become 41, and then gain margin is 14, which is what I am exactly wanting. So now the requirement, both the requirements are met. So this is the final plot of the design. Say 4, then save it. Let me save it. So if I copy paste that. So this is the final overall design that I have gotten for 12 degrees correction factor. And then my requirements both are meeting now. So if you see, my gain margin is about 10 dB, 40, and then phase margin is also 41 degrees. So in this way, we might have to tweak a little bit and then change the parameters slightly so that we'll be able to achieve the desired specifications. So just to quickly discuss the code overall, the design of the lag compensator using Bode plot. So in the beginning, I am uh, having this clearing of command window as well as workspace. Then I have defined the transfer function. Then I have gone to calculating the gain first from the desired steady state specifications. Once I got the gain, I am going to the lag compensator design. So first I have to see where is my phase margin requirement is meeting. Then with a 10 to 12% correction. So this is not reduction. This is rather correction term. So correction term and then later 12% correction term. I am calculating how much is the frequency there and how much is the gain of the plant there. So that much gain reduction will be given by the lag compensator, because lag compensator settles at 20 log 1 by beta. From there, I'm calculating beta and I'm considering T to be 0.1. And then I got the GC. Once I got the GC, I'm plotting G into GC and then checking whether my requirement is met or not. So in the first iteration, it is slightly short of 40 degrees. So I have made 2%, 2 degrees more correction. And then it is meeting. And then, sorry, this is not even percentage, it is degrees. And degrees correction. This is 12 degrees correction. So in this way, we are doing in an iterative way to design the lag compensator. So if you have any doubts, you can ask. Else, we can move to the lag lead or lead lag compensation. So in this case, we'll be having two such design criteria. So whatever we have followed in the root locus, same thing will follow. First, let us design the lead followed by the lag. So I will do in the same way. First, we have the transfer function, then Bode plot, what exactly is happening, and then we'll try to do. Okay, so here is my JC of S, which is K. Now I'll simply write K into 1 plus S T1. One is this S alpha T1 into 1 plus S T2 by 1 plus S beta into T2. Alpha is less than 1 and then beta is greater than 1. So we'll follow exactly one by one guidelines. First, we'll get the GC of J omega K into 1 plus J omega T1 by 1 plus J omega alpha T1, then 1 plus J omega T2, then 1 plus J omega beta into T2. And then same alpha is less than 1, beta is greater than 1. So in this way, we'll get the overall transfer function. And again, I have written one MATLAB code for the, let me close this. So Bode plot of lag lead. So same thing, I'm clearing the workspace as well as command window and all the figures. Then I have considered T1 to be 1 for the lag compensator part and T2 to be 10 for the, sorry, T1 to be 1 for the lead and T2 to be 10, which means 1 by T2 is 0.1. Same, whatever I have done in the lag compensator design, same thing, 0.1. And alpha to be 0.01, beta to be 10. And then I'm plotting this. So let us hope that it will plot. I think this is some issue with the laptop. I'm not sure what exactly is happening. Let me run it then how it is running. Share the screen again. Not sure this is a weird issue that I've faced. In the previous sessions, I have not faced this issue, but not sure exact reason. So this is the Bode plot that we will be getting. So initially there will be lag followed by lead and then again it will come back to 0. So if we want to discuss on this, let me write file dot lag lead Bode. So let us bring that to our notes. Okay. So let us have this over here. So we can actually change alpha, beta, and then see what is happening. But our point of interest is one region where the phase will be bound to become 0 because it is lag followed by lead. So it will become negative, then it will become positive. Means at somewhere it will become 0. So this is where the phase is becoming 0. So this is given by 1 by square root of T1, T2. So this omega is nothing but 1 by square root of T1, T2. Okay. So here, what are the design guidelines that we are going to follow? So guidelines. Again, always it's the same. First, design K of the controller using the steady state specification, steady state error gain specification or steady state error, steady state requirements or specifications. Then two, here guidelines are simple. First design K, then first design the lead compensator followed by lag compensator. So design lead compensator, then design lag compensator. Okay. So once we design, then check the Bode plot of GC into G, whether it is meeting the requirements. If not, if no, then redesign. So just to be on the safe side, now what I'm going to do is I'm going to take a slightly higher correction factor rather than doing it again and again, because individually we have done, but when we are combining both lead and lag, the permutations and the possibilities will increase. So just to be on the safe side and not risking redesigning, I'll try to take the correction factor slightly on the higher side, because we are slightly over designing but not too much. So let us solve one problem. And this is the planned transfer function that I have given. G of s is 1 by s into 0.1 s plus 0.2 s plus 1. And then these are the desired specifications. KV should be 30-second inverse. Phase margin should be at least 50 degrees. Bandwidth is at least 10 radians per second. So let us start from the step-by-step guidelines. First one is always finding the K. So my KV, which is 30, is nothing but limit s tends to 0 s into k into g of s. So if I calculate, I'll get 30 is nothing but k by 1, which means my k is 30. So I got the gain of the controller, which is 30. So now I'll go into the lead compensator. So before that, let us first see the code that I have written for the lag lead compensation using the Bode plot design. So this is the design, again clearing the workspace, everything. This is my transfer function, 1 by s into 0.1 s plus 1, 0.2 s plus 1. Desired is 30, phase margin is 50, omega desired is 10. And then this is the KC. Let us see whether the KC is coming to be correct or not. KC is 30. So again, the code remains same. First lead compensator followed by lag compensator. But before going into the code, let us go back and see what we have done for the lag compensator. So now we'll be relying more on the MATLAB and relying less on the math or hand calculation. So I'll start with the lead compensator. So first we have to draw the Bode plot and then see my phase margin, how much additional phase boost I need. Once I get that, I'll calculate alpha. Once I calculate alpha, I'll calculate the magnitude that is caused by the alpha because of the addition gain that the compensator is causing. Now I have to choose that frequency where exactly this negative of gain will be given by the planned transfer function. So that will become my gain crossover frequency. And once I calculate that, gain crossover frequency omega m, I can calculate my t. Once I calculate t, I'll do the uh, Bode plot or draw the Bode plot of the compensated and then see whether it is meeting or not. So let me do this part until this part. So first we have to plot G into Kc. So let us let me see, let us hope the Bode plot will run. It is not running. Let me stop sharing, run it and then reshare. Okay, so it has run. Let me reshare my screen. Okay, so this is my uncompensated plant multiplied by gain. So this is the phase margin, which is minus 17.2. And then how much do I need in the question? In the question, I need 50. So 50 plus minus 17.2. Or sorry, 50 plus this additional 17.2, 67.2 plus some 8 degrees I consider, say 75 degrees is the phase margin. I am considering a 17 minus 17.2, or I will add this also in the notes so that anyone who is going through the video later will be benefiting of them. So let me save the plot. Okay, so I am considering a correction factor slightly higher just to be, on the safer side so that I will not redesign it. So I'm having minus 17.2. So my phi m I am considering to be given is 50 plus first of all, this minus 17.2 should be made 0 because 50 minus 17.2 is 50 plus 7.2 plus I'm considering around 8 degrees. So 25 plus 80 around 75 degrees. 5M I am targeting, considering 8 degrees to be my correction factor. So this is the correction factor. 75 degrees is my 5M. Let us see how much are we getting. So in my code, same code. So I have calculated this 5M desired, and then let us see how much it is giving. It is giving 67. So I'm considering around 8 degrees to be my correction term. So now my 5M will be how much? 5M will be 75 degrees. Let us calculate alpha and additional gain. So alpha is calculated. Additional gain that I will be needing is 17.75. So from this, I have calculated alpha. Let us see how much is my alpha and how much is my additional gain is 17.75 dB. So now I have to find the frequency. Again, before that, let us see how much is the alpha. Alpha is 0.0168, 0.0168. So what we have to do, find omega m. Find omega m such that mod of G is equals to minus 17.75 dB. So we have to find the planned Bode plot frequency where we can get minus 17.75, so that will be cancelled with this. So I think I have closed that. Again, I have to stop sharing and then run it again. Sorry for the inconvenience. I'll try to figure it out by the next week. What is the issue? Okay. So this is what is our uncompensated plan has. Now what we are doing is we are trying to find out where I am getting minus 17.75. So that will be my new gain crossover frequency. That is the objective. So let us see minus 17.7. Minus 17.7. Yeah. So the frequency at which I'm getting minus 17.775. So I'll consider minus 17.8 or say minus 17.9. So I've considered minus 17.9. There I'm getting the frequency to be 21.8. So from here, Bode plot, I got omega n to be, how much did I get? 21.8 radians per second. So now calculate T. So we have to find T. So once we get T, then we can calculate GC lead. So first we are designing the lead compensation. So we'll be designing the lead. So let us see omega m is 21.8, whatever we were getting. So omega m is 21.8, 21.8. So again, the frequency corresponding to the negative of this gain, this is the frequency at which 5M occurs. So this is omega m. So I can calculate GC lead. So this is my GC lead. So once I have obtained the GC lead, again, what will I be doing? So I have done the second part of the compensator, lead compensator. So again, now I have to go to the lag compensator design guidelines. So lag compensator design guidelines says same. First plot K into G, or now we'll be plotting G into GC lead and then see how much decrement in the gain is required. Once I get that, I'll calculate beta, then I'll do this. So what I have done is this is done. So now I have to do the third part, which is the lag compensator. So draw the Bode plot of GC lead multiplied by GC, and then see how much decrement in the gain is needed. How much decrement in the gain is needed. The gain is needed. So once I get this, I'll calculate beta. I will assume my T to be 0.1 and then my compensation design is done. So I have the command over here where G into GC lead will be drawn, Bode plot both. and then we can get the Bode plot. So same issue. Let me stop sharing, run the Bode plot, and then start sharing again. Okay. So if I check this, so I have two Bode plots. One is the uncompensated one. So if you see the uncompensated one, here I have minus 17.2 degrees. And then with this, I have considered certain phase margin criteria, like I have considered 8% correction factor plus 40 plus minus 17.2 means minus or minus 17.2 to achieve 40 degrees phase margin. And if you see, it is not sufficient. I have reached a maximum of 23 degrees. So lead compensation, even with a correction factor of 8 degrees, is not sufficient in this case. So what I can instead do is, so this is my phase margin. So what I will be doing is, I will be trying to, this is my gain crossover frequency, how much it is, 21.7 radians per second. Now what I will try to do is, I will try to use lag compensation, and I will choose my gain crossover frequency somewhere here where my phase margin criteria is met. So which is what exactly the design guidelines said. What we are trying to do, we are trying to choose that omega where my phase margin criteria is met. So let us see how much I am targeting. 50 degrees, right? Phase margin 50 degrees I was targeting, and I could get only 23 degrees only. So lead compensation itself was not sufficient, and I have to choose 50 degrees means a correction term 12 degrees I'm choosing. So now I'll choose correction term 12 degrees. So 50 plus 2, 62 degrees. So 180 minus 62 degrees is 118 degrees. So I will choose 118. So this is the new, what do I call, omega c that I am targeting, and then with a correction factor of 12 degrees. So the frequency is 7.8. So at 7.8, I will see how much is my gain. 7 point. Yeah, close to this. So magnitude of 13.7 has to be decremented. Why it has to be decremented? Because my lag compensator will try to decrease that. So now this is my new frequency. Gain crossover frequency 7.71. So if this is my new gain crossover frequency, then this will be corresponding to my phase margin. So let us save this. This is the 7 lag lead Bode. Okay. So let us save that here. 7 lag lead Bode. Okay. So we have seen that this is with lead compensation, with lead compensation, and it was not sufficient because we have gone till 75 degrees. 5M. Maximum is 90 degrees. We have already gone till 75. And I need 25 more additional phase. But I can't cross 90 degrees, right? So it is not sufficient. So I have to go with the lead lag compensation as well. So it was not sufficient. I have already gone till 75 degrees. So this will say that I need lag compensation is required. Okay. For lag compensation, we know that we'll see that frequency where the I have considered correction factor. So I have considered around 62 degrees. So for the lag compensation, I have considered correction factor to be 12 degrees. Lag compensation, I have considered correction factor 12 degrees correction factor. 12 degrees correction factor. So that will result in 62 because it is 50 plus 12, that is 62 degrees. And then corresponding to that 62 degrees is this frequency 7.8. And that 7.8, I have seen that this is my magnitude. So this much decrement. So lag comp decrement in the gain, decrement in the gain will be provided by the lag compensator. So this will give my 20 log 1 by beta is minus 13.7. So 20 log 1 by beta is minus 13.7. So what is my beta? Minus 13.7. So let me go back to the code where I have the lag compensator. So first we are finding the frequency and then how much is the gain reduction needed. I am getting minus 13.7. So minus 13.7. So for this gain reduction, I have to calculate how much is my beta. So I got my beta to be 4.84, which is higher than 1. So my calculations, everything is 1. 4 point how much? 4.8417. 4.8417. Beta is 4.8417, which is nice. Now, T I am for this T I am assuming to be 0.1. It's a small guess. We are not designing basically. Trying to keep it closer to imaginary axis, just like a root locus. So I have done this T to be 1 by 0.1. So this is 0.1 inverse. Sorry, this is omega. So this is 0.1 inverse. Let me see if I have made the same mistake in lag. Did I make the same mistake? No, I guess. I think it should be fine. Yeah. T we are considering 1 by 0.1 because omega we are considering 0.1. So T will be inverse of that. Once we do that, then we'll get GC lag, which is 1 plus ST, 1 plus ST into beta. So once this is obtained, or maybe I should call this T2, and then this will be T2. This will also be T2. So that T and T2 will be different, or I can call this T1 instead. T1, T1. So that is T1 and this is T2. So just to avoid any confusion. So if I draw the Bode plot now, it should be able to meet. If it doesn't meet again, even after all this, I have to redo or redesign it again. So let me run it. So now I got the Bode plot. Let me initial my screen there. Yeah. So my blue color is the uncompensated. My orange color or red color is with the lead, and then my yellow one is the lag lead. So this is my phase margin, and this is my frequency. So my phase margin is now how much? 61.8 degrees, which is more or less fine because I needed 50 degrees. I am getting 60 degrees. So if I change the correction factor slightly smaller, then it should have been fine. And how much am I targeting the bandwidth? It is 10 radians per second. So first let me save this file, save as. This will be the 8th plot of the 8, save. And then we also have to plot the closed loop. So I will be plotting the closed loop. So Bode plot of feedback. So sir has mentioned that if you draw the Bode plot of the closed loop, it will be slightly higher. Bandwidth will be slightly higher. So feedback of unity feedback, right? This comma 1. Now whether it will plot this one. Is it plotting? Okay, I think it has plotted on top of this, but if I do it, it doesn't. Let me stop sharing and then plot it again and reshare. It did. Or let me reshare the screen. Yeah. So if I do the grid on and all stability margins, you can see minus 3 dB, right? So minus, yeah. So minus 3 dB is around 12.8 radians per second, which is okay. Let me increase the width of the Bode plot. 3. Yeah. So I'll also save this. This will be language 9th part with closed loop. Yeah. So what I am trying to do is first let me get the first picture. So I have designed it. I got this magnet Bode. Yeah, this is my overall final design where I have achieved a phase margin of 61. I needed 50. So if you want to reduce, you can play with the correction terms. So my phase margin is meeting 61.8 degrees. And if I also plot the other figure, the closed loop. So sir has mentioned that towards the end of the final lecture, that if my bandwidth of the loop transfer function is say x, the closed loop will be slightly higher. So for that reason, I have plotted the closed loop transfer function using the feedback command. And then this is the minus 3 dB bandwidth, which is coming 12.8 radians per second. So this is my closed loop bandwidth. So my closed loop bandwidth criteria is met. My phase margin criteria is met. And also the gain criteria is also met. So this is the gain criteria, whatever I am getting. So finally, I'll be getting my GC will be GC lead into GC lag, right? So GC will be GC lead into GC lag. And if I run this, and then if I do ZPK of GC, this is my overall lag lead compensation that I have obtained to uh, achieve whatever specifications they have mentioned. And if you can draw the Bode plot, you can get what exactly it is happening. But this is the overall idea. There is less than a minute. I think this meeting will end. Once this ends, I'll join back and summarize the session. But before that, I'll just explain the code. So I have cleared the workspace as well as command window, and then I have defined the transfer function and desired specifications. So first, always we'll be calculating the gain. Once we get the gain, we have to design the lead compensator. So first we have to see how much is the phi m that we need, and then we'll calculate alpha, and at that for that phi m, how much is the additional gain. So negative of this additional gain and what frequency that is happening will be my omega m. From there, I'll get my T1 and then GC lead. Now it is not sufficient. So now I have to reduce the gain so that my phase margin will be at that region where it is actually meeting. So I have considered phase margin to be with a 12% correction, and then I've seen how much gain reduction is needed. I have calculated beta. Once I have calculated beta, I have calculated the value of T2. Once I get T2, I will get GC lag. So now my compensator will be GC lead into GC lag. That will be my final GC. And then I have tried to plot the overall Bode plot to obtain what is my final design criteria, or whatever design criteria is being met or not. So if you have any questions, you can ask, else I will summarize this session. So this is the overall discussion for today. Uh, to start with, we have discussed about the lag as well as lead compensation. And then in week 8, we have discussed about the design using root locus, and week 9, we have discussed about the design using the Bode plot. And the overall objective is to design the compensator, and the basically lead compensator is used to improve the transient performance where phase is also leading, and then here 0 is closer to the imaginary axis. In the case of lag compensator, we are trying to improve the steady state performance, and here the phase is lagging and pole is closer to the imaginary axis. In the case of lead lag compensator, we are trying to improve both the transient as well as the steady state performance, and initially the phase is lagging and then it is leading. And it is a combination of lead and lag compensator, and we'll follow the same guidelines where we'll be designing the lead compensator first, followed by the lag compensator, and then we'll see the Bode plot whether it is trying to meet the design criteria or not. So in the case of lead compensation, we have seen alpha is playing a critical role in deciding phi m, omega m. So these are the relation between omega m, alpha, omega n and phi m, as well as the magnitude at this phi m with respect to alpha as well as t. So coming to the first design guidelines for the lead compensation, here we are always trying to design the K first, then we'll try to draw the Bode plot of KG, where we'll get the phase margin, bandwidth as well as gain margin. And once we are getting that, we'll see what is phi m, omega m, as well as what is this magnitude. Then we'll try to calculate alpha and T based on the formula that we have gotten, and then we'll try to draw the Bode plot and see whether it is meeting or not. If no, then we'll try to redesign, which is exactly what we have done in the first problem, where I have considered one problem. First, I have calculated K, then I have drawn it. Then I have seen that how much is the mod g that is needed. So I will choose that omega where I'll get minus mod g. And once I have selected that mod g, I'll be calculating alpha as well as t. And then I have tried to redesign. And then I have seen that in the initial correction term, it is not able to meet that. So I have tried to redesign. So what happened is, this is the first design that we have tried to do, but it was not sufficient. So I have increased the correction term because it is slightly short of the phase margin that we are trying to achieve. Then I have slightly increased the correction term and followed the same design. And then here the design requirements are met. And I have attached the screenshot so that whoever is going through the notes, they need not run it, but I'll also be uploading the MATLAB codes as well. So this is the lag compensation design criteria. Here, we are mainly taking the advantage of 20 log 1 by beta. So basically here we are trying to decrease the gain so that the frequency at which my phase margin criteria will be met, I am trying to force it to become the gain crossover frequency. So this is the decrement that I'm making in the gain so that that frequency will become my gain crossover frequency. So first we'll be obtaining the gain K and then we'll draw the Bode plot and we'll see where my phase margin criteria is being met. So at that frequency, how much gain I need to decrease, that I'll be decreasing with the lag compensator, and then we'll be calculating the beta, and then we'll be assuming T to be 1 by 0.1, and then we'll be designing it. So here I've considered one question where I have gotten the K first, and then I have drawn the Bode plot, and then I have seen where my phase margin criteria is being met, considering a correction term of 10 degrees. I have seen at that omega what is the decrement I need in the gain. And then I have considered that, and I have considered beta, and then I have considered T to be 1 by 0.1. And then I have seen that it is slightly short of the phase margin that I am trying to achieve. So I have tried slightly increase the correction term, and then now I am able to meet the phase margin criteria as well. So in this way, we have to do it in an iterative way, and we have to take the data and then put in the code. So just by clicking the code, it will not design. You have to see certain values and then plug in the MATLAB code where I have commented out, so that value, once it is updated, it will be able to calculate the controller gain. So coming to the lead lag compensation, it will have both a lead compensation as well as lag compensation. So first, the design guideline says the same. First, we have to design the K using the steady state specifications. Then design the lead compensator, then design the lag compensator. So the Bode plot of again GC into G, it has to be checked. If it is not meeting, then again you have to redesign. So this is the example that I have considered where I have given the specification. First, I have calculated gain K, which is coming to be 30. Then I have drawn the Bode plot of K into G, and then I have seen my phase margin is negative and it is unstable system. So trying to achieve a 50 degrees phase margin with a correction factor of 8 degrees. I have achieved, I wanted to achieve 5M to be 75 degrees, and that for 5M of 75, I have calculated alpha, and then I have seen this alpha and 5M corresponding to an additional gain of 17.75 from the compensator. So I have to choose that omega such that the open loop will have gain of minus 17.75, so that this omega will become my gain crossover frequency. And then I have obtained this omega from the Bode plot, and then that omega is leading to certain T, and then I have drawn the GC lead into GC Bode plot, and then I have seen whether my design criteria is being met or not. So even with the 5M of 75 degrees, my lead compensation itself is not sufficient, which is necessitating the requirement of the lag compensation, because 5M can be maximum 90 degrees, right? It can't be above 90 because it's 0 to 90 degrees. But 75 itself is not sufficient, and I'll be needing an additional at least 27 degrees. So I'll be needing lag compensation. So targeting a correction factor of 12 degrees, overall 62 degrees, I choose this frequency to be my new gain crossover frequency. And for that, I'll have the planned gain to be 13.7. So now my lag compensator will provide a negative gain of minus 13, negative gain of 13.7. So this will become 0 dB and my new gain crossover frequency. So 20 log 1 by beta is minus 13.7. I got my beta, T2 to be 1 by 0.1. I got the overall compensation, and then I've seen that the phase margin is 61.8 degrees. And then if I draw the closed loop transfer function, I'm getting a bandwidth of 12.8 dB. So my design criteria is coming to be 50 degrees, where I'm achieving 62 degrees almost, and then bandwidth is 10. I am achieving 12. So slightly over designed, but just to be on the safe side, it is coming to be fine. So this is the overall summary of week 9, and I hope it was interesting. I'll also be uploading the MATLAB files as well as this note, so you can go through, and I'll try to upload the video by tomorrow first off, so you can go through this video as well. And if you have any questions, you can ask, else I'll end this session over here. Okay. If you do not have any questions, then I'll end this session over here. I wish you all the best for your assignment 7, 8, as well as 9. I know I'm going ahead by 2 weeks because I'll be attending a conference and I'll be out of station, but I'll be uploading the video, so you can always go through that. And I'll also be attaching the MATLAB files in my drive so that you can play with the MATLAB files and try to design it in the iterative way. And yeah, that being said, again, we'll meet in the next week with week 10 course material. And I'll try to include MATLAB if it is needed. And yeah, with that being said, if you have any questions, you can ask, else I'll end this session.
Thank you, sir.
So if you don't have any questions, I'll end this session. I wish you all the best and good night.